Hey everyone, now I'm going to talk about our sixth and final challenge, quantification. So we've looked at many of these technical challenges in detail, but in quantification, this is perhaps a challenge that encapsulates all of these previous challenges and aims to perform an empirical and theoretical study to better understand heterogeneity, cross-modal interactions, and the multimodal learning process. This challenge should be done in context of all the previous challenges in order to get a better understanding of why our multimodal learning models work the way they do. So you looked at heterogeneity. In this case, the goal is to quantify all the dimensions of heterogeneity in these multimodal datasets and how they subsequently influence modeling and learning. If you recall from the introduction, we've seen all these dimensions of heterogeneity, such as the structure between modalities, how the representation space differs, the information content, their precision, the different noise topologies, and relevance to their task. How can we actually gain a deeper understanding of these dimensions of heterogeneity in the context of a learning problem? So this is a very understudied topic, but just to give a small glimpse of what are the possible opportunities of this understanding heterogeneity in multimodal data. So one big part is that of modality biases. When you're training with multimodal data, sometimes we see many unimodal biases which cause certain modalities to dominate and other modalities to collapse. So this related to the fact that different modalities have different information content and different relevance to the task. So one good example of this is that in these typical VQA datasets, you're going to start collecting images and questions from the internet and from annotators. And you might get annotators who ask questions like, what color is a banana? And because of biases, where 80% of the banana images on the internet are yellow, you're also going to see that 80% of these questions are going to be answered as yellow. So when you see a rare occurrence, such as a green banana, you're also going to start answering yellow instead of green. Here's an example, and that's an example of modality biases. And there's quite a few approaches of tackling this. This question is by no means solved. One simple approach is conceptually simple but very difficult to implement, is just simply to balance your modalities. Right? If you see is the umbrella upside down, and most of the times it is yes, you can also put more examples of umbrellas not being upside down. So that's more balancing a dataset, and this is a contribution of the VQA 2.0 dataset that basically took all of these questions and tried to balance the answers between yes and no and between the other possible answers. Another case is to balance training. I'm not going to go into too much details on this, but there's also many ways of kind of balancing your training objectives to ensure that you're not relying simply on unimodal biases, like in the image, but also to make sure that you attend to the question. So modality biases, beyond that, it's okay to kind of get the colors of your bananas wrong sometimes. But sometimes this can also cause more dire consequences, such as the fact that this can also be gender biases or social biases resulting from modality biases. So one example here is that you're trying to do image captioning, and you see this woman in the image along with the computer, but some of the image captioning methods that have been trained on this dataset simply look at a computer and infer that it's a man sitting in front of a desk. And these are capturing gender biases between the image, the objects in the image, and the caption. And you would like our models to actually be right for the right reasons, right? When it's generating a woman sitting in front of a computer, it actually looks at a woman. So there's many of these biases that have been found, and there's been certain approaches on tackling them, but still it's not by means comprehensive, and this question is by no means solved. So these are biases that come from unimodal biases. They can also be biases that result from cross-modal interactions. So this paper basically found that if you start looking at these image and text tasks, and you look at what the person is carrying, it looks at the image and identifies that it's a woman, and immediately starts assigning higher probability to carrying a purse instead of a briefcase. And one important thing that they found is that you can either measure these biases just by language, the person is carrying a blank, or you can also measure these biases in the context of both language and the image present. And they found that having the image basically worsens these social biases. So visual information actually makes the model more confident in reinforcing these gender stereotypes. So these are biases that result from cross-modal interactions. So there's modality biases. Biases that result towards having a better understanding of these dimensions of heterogeneity, especially towards information and relevance in modalities. Another big dimension of heterogeneity is the fact that different modalities can also have different noise topologies. So then how can we better measure whether our models are robust to these noise topologies in our different modalities? So one contribution in this paper was to first identify different ways that modalities can be noisy. So for example, really looking at the modality-specific and domain-specific ways in which noise can be introduced to your modalities. And that can be through typos in natural language, image and camera blurs in your visual modality, and if you have time series data, the fact that contiguous sequences of time can be dropped out in these modalities. Another type of imperfection can occur at the multimodal stage. It is known as multimodal robustness, where entire modalities can be missing entirely, or if you have correlated modalities across a time dimension, having all modalities missing across that chunk of time. So this paper essentially contributed all of these tests for testing whether modalities are robust in the presence of these modality-specific or multimodal imperfections. And a key takeaway is that, it shouldn't be surprising, there's a very strong trade-off between performance and robustness. Models might perform well, but they very slowly become not robust as you increase the presence of these imperfections. And subsequently, there's been some categories of approaches of making sure that your models are more robust. One general way is to simply introduce these imperfections during training. So normally I'm just going to train with my modalities XA and XB. They're perfect. I'm going to train them to make a prediction. And what if I also drop these modalities individually and make sure the model is still robust in making a prediction? What if I also introduce these imperfections to the modality and make sure they're still robust in making a prediction? So these all fall under categories of robust data and training. And the more exposure these models have to these imperfections during training, the more robust they can get when you're testing these models. There's also a second class of methods which aim to infer missing modalities by learning perhaps a translation model from A to B to infer when B is imperfect, or learning a joint probabilistic model that is able to impute B probabilistically when B is imperfect. And again, I'm not going to get into many of these details, but there's several references here that you can look at for cases in both robust data and training, and also to infer missing modalities. So that's just a glimpse of different dimensions of heterogeneity that might exist. Again, we just looked at information, relevance, noise. There are many other dimensions of heterogeneity that could be looked at. But another big sub-challenge is to get a better understanding of the cross-modal interactions. So if you recall, these cross-modal interactions, they capture connections between modalities, and these can be in the form of correspondences, basically referring to the same concept, dependencies referring to different concepts, and also the structure of these connections. And cross-modal interactions look at how are the interactions that result from the connections between these elements. And there's many definitions of cross-modal interactions. Again, how can we take these multimodal data sets and train models and quantify the presence and type of cross-modal interactions that are present? And again, this is a very big challenge. There's some glimpse into possible work. One big area of work is to build upon the idea of statistical interactions, which states that you have two features. If they cannot be decomposed into the sum of these unimodal functions acting on these individual features, then there are some cross-modal interactions that exist. And the first sub-challenge of representation, we've already seen a glimpse of how this can help. How we can take an arbitrary function f, perhaps learned through these multimodal models, decompose them into these unimodal subfunctions fa and fb, and looking at the residual. And the residual mu basically measures the amount of cross-modal interactions that exist in these models. So if these additive models is equal to the nonlinear, the diffusion models, then these non-additive interactions are not modeled. Otherwise, mu captures the overall quantity of the cross-modal interactions on this trained data set and models. This is good. This is a good sanity check for checking your models. You have trained a multimodal models. You always try to decompose it into a sum of these best additive models and look at the residual, this gives you a sense of the overall quantity of the cross-modal interactions on a whole data set and a whole model. But what if you want to go deeper? Instead of just the overall presence, can we also look at the individual cross-modal interactions that are in the data set? So one insight that we have is that if f exhibits interactions between two features beyond these additive interactions, then the second derivative of f with respect to xa, your first feature, and xb, your second feature, must be non-zero. So that's clear from the definition of non-additive interactions. So given this definition, this also inspires a natural second-order extension of your gradient-based approaches. So in other words, if I have a task, such as Clever, VQA, Flickr, all these QA or retrieval tasks, can I take the output of my model, take a first derivative with respect to some parts of the question, and then take a second derivative with respect to parts of the image. So that should then tell me the parts of the image that correspond with those parts of the question. And this method is actually pretty effective. You can take the parts of you can actually see that on Clever, the model does attend to the tiny yellow shiny object as the correspondence for the words tiny yellow shiny object. And likewise, you can do that for VQA. It does attend to the word birds as a second order interaction of the text birds, and likewise for 3 small dogs. So these are ways of identifying these corresponding cross-modal interactions in trained multimodal datasets and models at a very specific level for individual data points. One interesting thing is that you can also do this for other datasets that don't capture corresponding interactions, but rather complementary interactions. So over here on the Mosaic dataset on classifying sentiment and emotions, you can see that if you take the first gradient with respect to the sigh and the word sad, this can also capture the second order interaction with the lip movements of the speaker when saying those things, like the sad lip movements. So it can also help us to identify certain complementary cross-modal interactions. And there's certain other ways of capturing these cross-modal interactions beyond this one. So this paper called M2 Lens goes into a deeper perspective, essentially taking a model and taking methods to judge unimodal importance of these models. So that gives you the influence of your first modality and influence of your second modality. And this can be done using any unimodal interpretation method, like gradients or Lime or Shapley values. And then you can start doing analysis on these cross-modal interactions. And their insight was that if, based on these influences, you can then categorize the cross-modal interactions. If the influence of one is much larger than the influence of the other, that's a dominance type of interaction. If the magnitude of both are roughly similar and they also point in the same direction, that's a complementary type of interaction. And if the magnitude is similar but they point in opposite directions, that's a conflict type of interaction. So that's one way of also kind of interpreting these cross-modal interactions proposed by this approach. And one interesting thing they found that, is also kind of backed up by intuition is the fact that language is typically your dominant modality in predicting sentiment. Usually we look at what people say, and very rarely, but it's still in certain cases, we also want to look at what they gesture and how they're speaking. And they also have a very cool visualization website that is publicly available that allows you to look at to upload these videos and look at how these multimodal interactions exist in these videos. So these are mostly modality and model specific approaches. What if you want to go into more specific approaches for specific models that you've trained? So you do have a multimodal transformer. This recent paper also proposes an interpretation tool for these multimodal transformers, vision language transformers, specifically looking at these interactions. So essentially you can take these attention maps across your concatenated image and text data, and that can be broken down into 4 things. Your vision to vision attention, which basically tells you unimodal image importance, and your language to language attention, which tells you importance inside your text. And you can see that, indeed, just by looking at image importance, you see the surfer, and you also see the text importance of surfer and riding in a wave highlighted in text. You can also go deeper and look at the other two parts, which are your cross attentions, your vision to language attention and your language to vision attention. And then you can go deeper and start seeing that if you take the word, the attention from image to the surfer, you are highlighting the surfer. So this highlights the correspondence and complementary interactions across image and text. So again, there's this cool interactive website that you can check out if you want to play around with these models, interpretation methods. So one very big challenge here, these are a glimpse of the approaches on interpreting these cross-modal interactions. But one very, very big challenge here is how can we evaluate whether we're successful at interpreting our models. And this is difficult because we typically don't have a ground truth of these interpretations. So there's several ideas. One idea is perhaps do model simulation. So given a black box model, can we interpret it into some set of evidences and then give it to a human? And given these evidences, can a human then judge what the model predicted? And this should be in line with what the model actually predicted. So on one hand, if the model was fully black box and you didn't do any interpretations, the human should not be able to recover and simulate what the model predicts. But if your interpretation approach is completely faithful to the model, then you should be able to recover what the model predicts through human simulation. So that's a model simulation idea. Another idea which could be more practically useful is that of model debugging. Again, can we take a black box model, run some interpretations, obtain some evidences that what the model is using to learn, give that to a human, and let the human try to find certain bugs in a model, right? Is the model failing at one of these stages? For example, is the model failing at finding out cross-modal interactions? This can then be used to fix bugs and eventually obtain better measures of performance. But again, there's many open challenges here. Is the model actually faithful? Are the explanations actually faithful to what the model actually learns? It's also unclear if it's actually useful, if these explanations help humans. There's papers that show that they are useful and also papers that show that they aren't useful. One big issue is that of also disagreements. So you can run the same model on different interpretation method on different times, you can actually get different explanations. So how do you actually resolve this disagreement problem? And all of this should be studied in the context of how can we best evaluate these interpretation methods. So another big challenge is that of the multimodal learning process. We've seen many dimensions of heterogeneity, we've seen issues of cross-modal interactions. But when we bring these together, are there any learning and optimization challenges involved in learning from heterogeneous data? And the answer is there are. We will expect that adding more modalities should always help, but people have also found that adding more modalities may not help. In this case of kinetics, we're trying to do classification from RGB video, from audio, and from optical flow. Sometimes adding more modalities actually hurts performance. And one core finding they have is that if you have all these modalities, they learn at different rates. Some modalities are easier to learn from, and they more quickly learn and overfit. And some more modalities are more difficult to learn from, and they start learning from it, and they take longer, so they don't actually learn from that modality. And again, this challenge inherits from the idea of these different modalities having different dimensions of heterogeneity that affect how much information and content that they have. And they propose certain ideas. I think none of these are fully solved the problem, but one idea that they proposed was to actually keep track of how much each modality is learning from your data and overfitting, and therefore try to balance the learning rates of each modality such that they are better balancing training across your modalities. One big issue here is that instead of just training one multimodal model from your modalities to your data, you actually have to train a multimodal model, but also train these unimodal models to keep track of how each modality is learning. And that can be a bit slower, but it allows you to kind of simultaneously balance the learning rates across your modalities for better balanced training. But still, many open challenges in learning, in optimizing these multimodal models. So we've just barely scratched the surface. We have seen issues in heterogeneity. How can we better quantify it? How can we better understand the presence and types of cross-modal interactions? And how can we better optimize our models? There are still many challenges in each one. And more importantly, quantification should be an overarching technical challenge that aims to revisit each of these previous 5 challenges. How can we understand heterogeneity in learning representations? How can we understand the interactions in the reasoning process? How can we understand the learning challenges in generating multimodal data? And with that, all of these are almost open questions. And if this slide overwhelms you, the idea is that it should. Quantification is perhaps this overarching challenge that looks at the core challenges of multimodal and also looks at the core sub-challenges and aims to look at, quantify how each of these should operate. So a lot of open challenges over here. So just to conclude, we have seen many core multimodal challenges. We started with representation and alignment. Representation, the idea of capturing heterogeneity in your data and learning representations that summarize this heterogeneity. Alignment, the idea of capturing the connections and dependencies between your modalities at both local and global levels. And these 2 sub-challenges are perhaps present in all multimodal problems. Once you capture representation and alignment, can you actually use that to better inform a reasoning process? A structured way of doing multi-step inference, ideally with interpretable concepts that capture either domain and external knowledge about your multimodal problem. Sometimes you might do explicit reasoning to get a prediction, but sometimes you might also want to do explicit reasoning to better generate multimodal data or to better transfer knowledge from one modality to the other. And of course, we don't do reasoning all the time. It would be great if we did, but sometimes you might just skip from representation and alignment to whatever your end task is, whether prediction, generation, or transference. And finally, quantification is this overarching challenge that revisits all of these previous challenges and tries to get a better understanding of the learning and optimization challenges in these multimodal methods. Again, this is just a very small glimpse into the whole spectrum of multimodal research. Coming soon to an archive near you, we're going to release this very new survey paper that captures these, that goes into more in-depth into this taxonomy, captures more sub-challenges, and also surveys more than 600 papers that are relevant in this area. If reading papers isn't your thing, we also have this full multimodal machine learning course at CMU with course content readily available alongside lecture videos, as well as an advanced topics course that goes deeper into some of the open challenges and open readings in recent times. So that's the end of our talk, that's the end of our tutorial. And if you want to capture something, is the fact that multimodal is the science of heterogeneous and interconnected data. All right. Thank you, everyone.